Welcome to The Explainer. Today, we're going to demystify those super complex electrical yards you see all the time but probably don't think twice about. We're heading inside to really get a handle on the incredible engineering that keeps our lights on.
You know, they kind of look like these crazy metal jungles, just full of strange equipment, humming away. But they are not just a random collection of hardware. They have an absolutely crucial purpose in our daily lives. So, what exactly is their job?
The best way to think of them is like critical interchanges on a massive electrical superhighway. They're managing the flow of power that literally keeps our world running. They direct it, they protect it, and they transform it on its journey to your house. Okay, let's dive into this.
So we're going to follow a single pulse of electricity on its journey, starting right at the entrance to the station. This is where it meets its first, and you could argue, most important security checks.
Okay, so the first huge challenge is protecting this multi-million-dollar facility from one of nature's most powerful and unpredictable forces. A direct hit from lightning could be, well, catastrophic. So the whole system needs a bodyguard.
And this device is that front gate security. See, under normal conditions, it's just like a closed door. But the second a massive surge, like a lightning strike, hits the line, that door flies open and it instantly diverts all that dangerous energy safely into the ground. It's the essential bodyguard protecting all the other expensive equipment down the line.
Now, here's something you might not know. Those high-voltage power lines, they also double as communication lines for the grid. It's a really clever way to send vital grid management data between substations. But those data signals can actually interfere with all the sensitive equipment inside the station.
This is just a brilliant example of how the system separates two totally different jobs happening on the same wire. The wave trap, it acts like a bouncer at a club, right? It's checking the frequency of everything trying to get in. It lets the low-frequency power cruise right on through, but tells the high-frequency communication signals, nope, you're not on the list. This ensures they don't disrupt the main event happening inside.
You can't just walk up and plug in a standard multimeter. I mean, the sheer force of that electricity would instantly vaporize it. You'd need impossibly huge and, frankly, ridiculously dangerous equipment to even try to measure it directly. So, how do they do it?
Well, the solution is just ingenious. You don't try to measure the giant, you measure its shadow. These special instrument transformers create these small, safe, and perfectly proportional little copies of the voltage and current. So CVTs shrink down that massive voltage, and CTs reduce the huge current to tiny, manageable levels that all the standard meters and the station's own protection systems can handle safely.
Okay, so now the power is safely inside, and it's being measured. Next, it needs to be directed. So let's look at the components that act like the traffic cops of the substation, controlling exactly where all that electricity goes.
This thing right here is the system's ultimate protector. Yeah, in normal operation, it's just a switch. But during a major fault, it has to do something that sounds impossible. Instantly break a current powerful enough to level a building, and do it in just a few milliseconds without destroying itself. It's an absolutely incredible feat of safety engineering.
Now, this might look kinda like a circuit breaker, but its job is totally different. An isolator isn't designed to interrupt power at all. It's a safety device you use after the circuit breaker has already done its job. It creates a really obvious visible air gap that guarantees to any technician, hey, this circuit is truly dead and it's safe to work on.
And what's really fascinating here is just how different their roles are. The circuit breaker, that's your expensive, high-tech emergency responder. The isolator, on the other hand, is the cheaper, much simpler tool that you use for planned work. They're two different tools for two very different jobs, but they absolutely have to work together perfectly.
And this is exactly how they do it. It is a precise, non-negotiable sequence every single time. First, the circuit breaker cuts the power. Only then can the isolators on either side be opened. This safety handshake makes sure there's zero chance of an accident, and it's a critical procedure in every substation out there.
Okay, we've now arrived at the very heart of the substation. The massive, humming piece of equipment that is, really, the main reason the whole station even exists in the first place.
This single piece of equipment represents the biggest investment in the entire yard. It's the most critical component, and honestly, everything we've looked at so far pretty much exists just to protect and serve this one thing.
So here it is, the power transformer. This is the component that does all the heavy lifting. See, it's way more efficient to send power over long distances at super high voltage, but it's way too dangerous to use it at that level in our neighborhoods. So this transformer's primary job is to step down that voltage to a more manageable level for local distribution.
And this
This just shows you the sheer scale of the change we're talking about. This one transformer takes in a lethally high 145,000 volts and drops it down to 36,000 volts for the next stage of its journey. This right here is the core function that makes our entire grid work.
All right, finally, let's look at the components that literally hold this whole system together. They might not be the stars of the show, but trust me, without them, the whole thing would just fall apart. These are the nuts and bolts of the grid.
And here's a cool bit of trivia for you. The massive cables, the conductors, that carry all this power, they have a kind of strange naming convention. They're often named after animals. And the fun rule of thumb is, the bigger the animal, the bigger the conductor. So a moose conductor is going to be much, much thicker than a dog conductor.
These might just look like simple stands, but they play a super critical structural role. The main conductors, or bus bars, are incredibly heavy. So without these strong, insulating supports, the physical strain of all that weight would actually crack and destroy the connection points on all the expensive equipment, causing a total catastrophic failure.
So, let's just trace that journey one last time. The power came in, it was protected by its bodyguards, the arrestor and wave trap. Then it was measured precisely. After that, it was routed by the traffic cops, the breakers and isolators, before it finally reached its main destination, the giant power transformer. There, its voltage got stepped down, ready for the next leg of its trip, all of it supported by this physical network of conductors and insulators.
It's really an incredible feat of engineering, isn't it? It's this complex, coordinated dance of components that we all rely on every single second of every single day. And when you see how it all fits together, it really makes you appreciate not just the complexity, but also the fragility of the system that powers our entire modern world.